Welcome back to the course of chemical crystallography. In last few lectures, we were discussing about the theoretical aspects behind the data reduction. As you already are aware that a raw data, which is nothing but a set of images which was recorded using some two-dimensional area detector, and those images contain the X-ray intensity from the diffracted beams coming out of a given crystal. So, whenever a diffracted beam meets the detector, it creates a signal there, and that signal is just the raw intensity, which has to be corrected for various factors. As you have already learned that we need to do a correction for the incident beam intensity. Depending on beam intensity, the diffracted beam intensity will vary. Then we have learnt about the exposure time and its effect. Then we have discussed about the Lorentz and polarization corrections in the previous class. And in the previous class, we have seen that Lorentz and polarization corrections are must for data collections using a diffractometer and if you are using a crystal monochromator. So now we should concentrate on a different aspect on data reduction, which we call as the absolute scaling and the effect of temperature factor. If we assume the atoms are spherical in nature, so with the assumption that the atoms are spherical, the scattering factor of an atom, that is F of an atom, varies with sin theta by lambda in the following fashion, as you already know. F versus sin theta by lambda when it is plotted in terms of angstrom inverse unit. This corresponds to the value Z of the atom in concern. So, if it is carbon, so if we are plotting atomic scattering factor of carbon, then this point is 6. So, as we know that if we have an atom in the crystal and it is considered to be spherical, at any given temperature the atom has thermal vibration along X, along Y and along Z. So, because of this thermal vibration, the electron density is no longer spherical, is rather diffused over a three-dimensional space. So, when this electron density is diffused, then the diffraction from a given plane having several diffused electron densities at different places will have a certain intensity of diffraction. When the X-ray hits the plane and gets diffracted, it will have a certain intensity of diffraction, and with temperature, by reducing the temperature, when the atoms are more confined towards its nuclei, the electron density on this plane is more tightly bound. As a result, the intensity of the diffracted beam at low temperature, ILT, will be greater than IRT. So, this effect has to be incorporated in the expression for the actual scattering factor F of any atom. It is very clear that at high temperature, these vibrations will be more significant, and hence will influence the diffracted intensity more. And also this thermal vibration depends on the mass m, mass of the scatterer or atom. Because the heavier the mass, lower is the vibration. So for heavier elements, thermal vibration is less, and for lighter atoms, the thermal vibration is more. And then also depends, the thermal vibration depends on how an atom is bonded in a molecule. Suppose if we have an aromatic ring with 6 carbon atoms with alternate single and double bonds, they are more tightly bound to each other. They have constraints in their bond length and bond angles. As a result, the thermal vibration for every individual carbon on aromatic ring is restricted, while if you have an hexane chain having 6 carbon atoms, they all have a fixed bond length, but they have a flexible bond angle which can change, and you can rotate the bond without breaking or making a new bond. So these bonds are more flexible. As a result, it is possible that these atoms can vibrate more freely compared to the other one. And then in case of some groups like this, which is a trifluoromethyl group, when you have 3 large highly electronegative elements bonded to a carbon, these 3 electronegative elements repel each other, that is electrostatic repulsion. Associated with a thermal motion of these fluorines, the electrostatic repulsion in between these fluorines will result into a situation where it will look like there are multiple fluorines connected to the central carbon atom. Because this group is vibrating in such a way that it is as if doing is like a rotation. So this thermal vibration makes the scattering from this type of compounds very weak, very feeble, and hence we need to take care of that kind of thermal vibrations. So the effect of thermal vibration is to reduce the scattering power of an element, mostly lighter elements, and hence the diffracted intensity is weak. The result of thermal vibration is lowering of scattering factor, which means if this is the scattering factor curve for an element without the thermal vibration, the same atom would have a scattering factor varying like this with thermal vibration. This variation in atomic scattering factor, this change or variation in atomic scattering factor is given by e to the power minus b sine square theta by lambda square, where b is equal to 8 pi square mu bar square, where mu bar square is equal to the mean square amplitude of atomic vibration. So the actual F is equal to F observed multiplied by e to the power minus b sine square theta by lambda square. So if we try to plot e to the power minus b sine square theta by lambda square versus sine theta by lambda in angstrom inverse unit, we would get a straight line when b is equal to 0. When b is 2, we get a line like that. When b is 4, it is more severe, and when b is 8, this decreases significantly. As a result, the corresponding plot for atomic scattering factor F with sine theta by lambda plotted in angstrom inverse unit should look like this. This top plot is without the thermal vibration, that is when b is equal to 0. But then with high increase in the value of b, this curve reduces quickly. That means the atomic scattering factor of the element reduces significantly with larger and larger value of b. And so on. So that means on reducing the temperature, we approach from higher value of b to lower value of b. This is the direction of lowering the temperature T. So when you lower the temperature, the mean square displacement of every atom decreases. As a result, the atomic scattering factor reaches its actual value when there is no thermal vibration. So this correction has to be incorporated for each and every reflection in a particular data when we are collecting at a given temperature. So we need an estimate of this thermal parameter B from the measurement. Now we need to define the average observed intensity corrected for Lorentz and polarization factors. That I rel is equal to the average of F relative square. So if you have an unit cell with n atoms, then we can show that I absolute is equal to sum over I equal to 1 to n Fi square, where is the theoretical average intensity. And this IABS depends on the atoms present and number of such atoms present. It is independent of the positions of the atoms. So, the ratio IABS by IREL should be defined as the scale factor to place the I relative values on an absolute scale. But we have few problems. Number one, Fi are not same, and by means same, that is not same over the range of sin theta by lambda. It is dependent on sin theta by lambda. So, IABS also varies with sin theta by lambda. This effect, which is coming here because of the value of f being not constant over the entire range of sin theta by lambda, it being changing with sin theta by lambda, IABS also varies with sin theta by lambda. So, to avoid this, we divide the Ewald sphere into small infinite shells such that the value of Fi do not change within a shell. And the second problem that we encounter is that, as we already discussed, Fi are all influenced by the thermal motion. So, actually what we should write for IABS average as the sum over I equal to 1 to n FOI square e to the power minus 2b sin square theta by lambda square. assuming same value for B of V for all the atoms. So we can rewrite this expression as e to the power minus 2b sine square theta by lambda square into sum over I equal to 1 to n FOI square. So now, if I relative is equal to the scale factor C multiplied by I abs average, then we can write it as C into e to the power minus 2b sine square theta by lambda square into sum over I equal to 1 to n FO of I square. So we can rearrange this equation like this: I relative divided by sum over I equal to 1 to n FOI square is equal to C into e to the power minus 2b sine square theta by lambda square. By taking natural logarithm on both sides, we can write ln I relative by sum over I equal to 1 to n f0 I square equal to ln C minus to be sine square theta by lambda square. So now if we try to plot the left hand side as y and this as x, what do we get? On y axis we are plotting ln I relative by sum over I equal to 1 to n FOI square versus sine square theta by lambda square like this. So what would we get? We would get a straight line with negative slope. If we extrapolate that straight line to sine theta by lambda whole square equal to 0, that is at 0 degree angle of diffraction, this intercept would give us the value of ln C, and the slope here will be equal to minus 2b. So we can then calculate both the scale factor and the temperature factor from this measurement. So if you write this in this manner now, I relative is equal to C I abs. So I relative is nothing but mod of F relative square is equal to constant C mod of F abs square, which means amplitude F abs equal to 1 by root over C F relative, which we can rewrite as K into F relative. So, we can establish a relationship between the absolute structure factor amplitude with the relative structure factor amplitude with a constant quantity K, which is written as the scale constant. So, this is how we can get the value of the absolute structure factor amplitude from the relative values using a scale constant for a given data. So, this method of scaling is applied in a data reduction program, and then we generate this plot which is called the Wilson plot. So, the feature of an Wilson plot is supposed to be a straight line with negative slope if we are plotting these two quantities, and this straight line with negative intensity should have all the reflections falling very close by this straight line like that. So, these reflections should represent a linear distribution with a negative slope. If in case we encounter with a data set where the intensities are scattered like this and a best fit straight line cannot be drawn, that means there must be something wrong in the data. Probably you have not determined the unit cell correctly, and you are not considering this required number of atoms inside the unit cell and so on. So, those corrections then need to be checked, those parameters need to be checked at the time of data reduction. So, this is how we can handle a raw data and try to process it for the next step, which will be the determination of symmetry, whether it is having a centrosymmetric distribution or a non-centrosymmetric structure, or whether it has a two-fold or a mirror plane. So, these things we will discuss in the next class.